In the first video, I've shown you the general overview of the Synopsys Custom Designer workflow in circuit design and layouting for masking. In this video, we'll walk through the process of creating a simple CMOS inverter. This video will cover schematic capture of a simple CMOS inverter using Custom Designer Schematic Entry Tool and the design of a simple test bench. Finally, we'll work with HSpice simulation to test our test bench. Let's begin. First, we'll create a new library for this tutorial. Here, you can right-click and create new library. Let's name this library samples. We'll attach the technology TSMC 18RF, the technology we're going to work with. Let's press OK. Here in the samples library that we recently created, let's create a new cell. We'll call this cell the inverter cell. Let's click on the inverter and create a new schematic entry. In the new cell view, we select schematic and press OK. Here in the schematic entry, we can start creating our first inverter. There is a simple guide of an inverter in Wikipedia. This is the basic layout of an inverter, a PMOS and an NMOS. The input is distributed to the PMOS and the NMOS, and the source of both the PMOS and the NMOS is the output. So, let us begin by instantiating a PMOS and an NMOS in our inverter schematic. You can do this by pressing I from the keyboard, or you going to add and going to instance. Then we select the TSMC 18RF library and add find the PMOS. We'll be working with the 1.8 volt library of the TSMC 18RF, so we'll be using the PMOS 2 volts. In your application, you may be using a different library and a different voltage rating. In this video, we'll be using PMOS 2 volts. Once you click the cell, the view will default to symbol. You can then hover your mouse and choose a destination for this cell. Let's click here and then change this to NMOS. Once again, we'll add a new cell. Now we have a PMOS and an NMOS in our schematic. Next is we add a pin. Let's name this pin input IN, and let's put it in here. And then we'll make another pin output. Let's name it out. We must change the type to output and place it here. Then you need to add a wire. You can click here or press W from the keyboard. By the way, you can press P for pin. Some of the shortcuts are listed here. Let's click on wire and click on these points and distribute the input to the gates of both the NMOS and the PMOS. Then let's short out the source to the output. The next stage is to add the global VDD and VSS. To do that, let's press again on I to instantiate another cell. Let's use the analog lib and type in VDD. As you can see, we have now the VDD, but we're having difficulty with our schematic, so you can press F to take a full view and scroll outwards using the mouse scroll. As you can see, you can scroll. Then we need to put in the ground. Once again, press I and type in the cell ground. There we go. Then press on W to wire them. Now, depending on your design requirements, you may be required to put the bulk to the VDD. In this case, we'll put the bulk of the PMOS to the VDD. And let's put the bulk of the NMOS to the ground. As you can see, we have partially completed our design of our CMOS inverter. Now, let's proceed by assigning the proper lengths and widths for our NMOS and PMOS. You can press on the PMOS and press on Q. You'll be shown the property editor. Here in the property editor, you can minimize attributes and deal with the parameters. In the parameters, as you can see, the length is already set to the minimum for this library, the TSMC 18RF library. So the width is what we have to change. In this example, we'll be using the width of 18 times 2 times 3, and that is, using the calculator, 0.18 times 2 times 3. We'll use 1.08 micrometers. Let's copy this and paste it here. That will default to micrometers. And here, let's use the minimum times 2. The minimum, once again, is 0.18 times 2. That is 0.36. As you can see, we have now defined the lengths and widths of both our PMOS and NMOS. Note that W and L sizes will vary depending on the purpose of your design. Now, we'll begin creating a test bench for this circuit, but first we have to check if we do not have any errors. You can click this or press on Shift X to check and save. As you can see, the warning is nothing is bound to escape in the current active set, which we can ignore. There is nothing serious about the current error. However, if we do make a mistake, for example, if we cut this wire loose by pressing on delete and then checking, we'll have problems because this one is being highlighted. That means there is an error. If we click on here, it will show up. It shows up as that IO pin B of instant MO is floating. 0 errors but 1 warning. So we must correct that by putting a wire from here to here and pressing this one. As you can see, the highlighting is gone. Once again, press F to full view zoom and press escape to cancel any commands. Commands will crop up in here for your history and for the settings for each command. Make sure to check this area for any settings for any command that you made. Now, let us proceed by creating a test bench. But before we create a test bench, we must create a symbol for this cell. You can go to Design, New Cell View, and create From Cell View. This cell view is a symbol. We'll use the symbol editor. You can use the default settings from here and press OK. As you can see, we are presented with a symbol editor for the schematic we just previously created. You can safely delete some of these parameters because we don't really need them. A very simple symbol for an inverter is this one. As you can see, it is a triangle with a 0 at the output. This means that any inputs are inverted at the output. We'll create this one. It is as simple as drawing things on the canvas. So let's press C, select the rectangle, select the point from which our point of origin for the copy starts, and drag the mouse below. Now, select the shape and go to lines or path. Select from here to here, then there, to here. Double click to end your selection. Press D and delete the rectangle. Now we have a perfect triangle. Let's create a circle in here. It's as simple as dragging your mouse and clicking the end. Press Shift M to move an object. Now we have moved the circle in front of the triangle. Let us copy the pins by pressing C, selecting them, clicking the point of origin, and simply moving your mouse. To zoom in, use your mouse. Shift M to move. And finally, put that there. Press F to full view. Press Shift M once again and select the input pins. Now select the origin and move that here. Now we have a very simple inverter. Let us rename this cell name. Press Escape to escape from the move command here and double click on cell name. Let's name this inverter. Now Shift M and move this name here. We can now safely delete this first initial symbol, but make sure you leave this red box. Press Escape to leave the delete command and press M to stretch. Select this area and stretch it here. Select this area again, stretch it here. Now let's just make sure we have the minimum amount of space needed. Then select the edit and define the origin. Let's put the origin in the middle so that every time we rotate this symbol, the center of rotation is in the middle. Let's press F to center at it and press this one to save. You can also do F2 to save. Now you can safely close the symbol editor and close the schematic editor. Let us now create a test bench for our inverter. Let's create a new cell. Note that we are in the same library, the samples library that we created in the beginning, and let's create an inverter test bench. We usually name it inverter, the same name as the cell, but we append a test bench. Depending on the type of test bench, you may name it depending on your application. For this application, let's just name it underscore test bench and press OK. Let's create a new schematic here. Press OK. Let us instantiate by clicking here or from here or pressing I. Let us instantiate the cell that we just recently created, our inverter. Note that we're using our library, the inverter cell, and our symbol. Let's place this cell here. Now we'll place an analog VDD source. This will supply voltage to our internal VDD that we placed inside the inverter layout. V source and the ground. Let's also put a ground in here and use a V-pulse as an input. You can use R to rotate a cell. Press Escape to cancel this command. Press or Shift M to move this ground a bit to the left. So you can see we're using the grids to align the schematic in order to make them look good. Press W and wire them up. Note that we are leaving the output blank because we are using an open-ended test bench. Now let us name the wires in and click on this wire. This is the input, and name this one and name it as output. Now we'll begin setting the values for our voltage sources. Press escape to cancel the previous command and press on Q to open the properties editor. Make sure you go to the properties and let's just minimize attributes for a while. Let's press F to full view and click on this cell. This is a voltage source that pulses a V pulse. More information about this can be found on the HSpice manual, but for this experiment we'll use voltage 1.8 volts. Let's leave the V because by default they are in volts. The lay time, let's use 0.01 nano or 100 pico. Rise time 0.1 nano. Fall time 0.1 nano. Pulse width 2 nanoseconds and 4 nanoseconds for period. Anyway, let's delete this delay time. We don't need it. Let's put in 0 there. For source, let's put in a DC voltage of 1.8. Now, let us begin by checking if we don't have any errors for our design. Let's go and click here. You can see that we have one warning and the output pin out of instance IO is floating. This is the only error that we're having. That's fine for now. Now, let us begin by simulating this test bench. To do that, let's go to Tools, SAE, and begin initializing the parameters for this simulation. Let's go to Setup and Analysis. Let's use the transient analysis and time step of 1 femto. We will have a stop time of 12 nanoseconds. That means we would cover 3 periods because we have a period of 4 nanoseconds in our schematic. Press OK. Here in the expression, just click on the input, click this again, and click on the output. Let's also set the model files. Our model files is found in the home directory, Synopsys, Models, HSpice. Let's use the RF018L and use TT. Just press OK. Go to Sessions and then Save or press S. We will save this configuration so that in the future we can easily load it by pressing L. To begin simulation, go to Simulation, Netlist and Run, or just press Ctrl S. HSpice will begin simulating our project. As you can see, we have finished the simulation. This is custom wave view. We can click here for the input output and ungroup them. As you can see here, the input is inverted in the output section. To group them, click both by pressing on Shift and Group. You can then use this tool. You can set it for zoom in X-axis, Y-axis, or for both axes. Let's use the zoom for X-axis and drag the mouse from here to here. As you can see here, we have shown the inversion rate. You can go to Measurement tool and the rise time, fall time, and begin testing for the rise time and fall time. Just click on Apply, and if you drag this here, you'll be shown the rise time for the input, which is green, and click on Apply once again and drag this around. You can separate both in order to easily assign the rise time or fall time of both. You can see that the rise time is 80 pico for the input and we have a fall time of 35.7 pico for the output. We have shown you how to design your CMOS inverter using the schematic capture, how to design the test bench using the same tool, and using HSpice assisted by the SAE tool in order to simulate your test bench. This is it for this video, and thank you for watching.